The Solow growth model is an economic model for economic growth based on the level of labor, level of capital, and state of technology. The basic Solow growth model is the simplest form of the model. It is based mainly on the relationship between capital per worker and output per worker, with the main interaction in the model being that of saving rate and depreciation rate. To derive the model, we have to look at a number of components and relationship in the economy. The first component we are going to look at is aggregate production function. In this scenario, we will assume that output is based on two factors, which are capital and labor. We can say that output is a function of capital and labor. Y is equal to a function of K and N. This function represents output, capital, and labor at the aggregate level. However, we are more interested in the per worker form of this relationship, since output per worker or GDP per capita is more reflective of the standard of living in the economy. Than its aggregate counterpart. To convert the function to the per worker form, we will divide the function by n, or number of workers in the economy. Assuming a constant return to scale is y divided by n is equal to function of k divided by n and n divided by n. This equation can be rewritten as y equal to function of k and 1, then as y equal to function of k, where function of k is equal to function of k and 1, and y is equal to y divided by n, which is the output per worker or GDP per capita, and k is equal to k divided by n, which is capital per worker. The next component we have to consider is the relationship between saving and investment. The flow of economic activity shows that investment and government spending is equal to saving and tax, or I plus G is equal to S plus T. We can adjust the equation so that I is equal to S plus T minus G, where investment is equal to private saving and public saving. If we assume that the government operates on a balanced budget, government spending will be equal to tax. So that I is equal to S, this relationship can be seen when saving is channeled to investment when banks lend out their deposit as loan for purposes such as business investment. This relationship can be linked to output since saving is a function of output, where capital S is equal to SY, where S is the saving rate or the fraction of income that is saved. Because of the relationship I is equal to S, the relationship I equal to SY is also true. This means that investment depends on output. This relationship can be explained if we look at it as if income increase, people will save more and therefore there will be more money available for investment. However, this relationship is still in its aggregate form. To link it back to GDP per capita, we have to convert it to per worker form by dividing the equation by n. I divided by n is equal to SY divided by n equal to SY, where y is the output per worker or GDP per capita, because y equal to function of k, and I divided by n is equal to S function of k. The final component of the basic Solow growth model is depreciation. Depreciation is the loss in value of an asset as time passed. It is represented as depreciation equal to delta capital K, where delta is the depreciation rate or how much the capital stock wears out each period. In its per worker form, depreciation per worker is represented as depreciation per worker equal to delta little k. Now that we have all of the components, we can put them together. Depreciation and investment can be linked together through capital or capital stock. The capital K prime equal to 1 minus delta multiplied by capital K plus I, where capital in the next period, which is capital K prime, is equal to capital that has in depreciation, which is 1 minus delta multiplied by K, and investment from this period, which is I. This equation can be put in its per worker form by dividing by n. You will get K prime equal to 1 minus delta multiplied by K plus I divided by n. And since I divided by n is equal to S function of K, you get k prime equal to 1 minus delta multiplied by k plus s function of k. From this equation, we can come up with an equation for the change in capital per worker over time. A change in k is equal to k prime minus k. A change in k is equal to 1 minus delta multiplied by k plus s function of k minus k. A change in k is equal to k minus delta k plus s function of k minus k. Then a change in k is equal to s function of k minus delta k, where change in capital per worker is equal to investment per worker minus depreciation per worker. This relationship can also be called the equation of motion for k, and it determines the behavior of capital over time. This means that the equation will also determine other variables that depend on k, such as output per worker, which is y, since y is equal to function of k, and investment per worker as function of k. Graphically, this relationship can be represented as this graph. The intersection of s function of k and delta k is the point where investment is equal to depreciation. At this point, since the two values are equal, a change in k will remain at 0 and k will be constant. The economy is in the steady state at this point, and the value of k at this point will be constant, and is called the steady state capital per worker, denote k star. At the steady state, since the value of k star is constant, the value of output per worker, which is y star, which is a function of k star, will also be constant. If the economy is not at steady state, it will gradually move toward the steady state over time. This convergence of the economy towards the steady state can be observed in the graph. Since s function of k represents investment and delta k represents depreciation, the area between the two curves will represent the change in capital stock per worker, which is a change in k. At any point where s function of k and delta k are not equal, there will always be a change in k. If delta k is greater than s function of k, depreciation will be greater than investment, and there will be a negative change in capital stock per worker. This change will continue until it reaches a point where the difference between s function of k and delta k became 0, at which point the steady state is reached. The same applies to the case where s function of k is greater than delta k. At that point, investment will be greater than depreciation, causing a positive change in capital stock per worker until the steady state is achieved. Another point to notice is that the change in capital stock per worker, which is k, will become smaller and smaller the closer you are to steady state. If capital stock per worker initially starts far away from the steady state value of capital stock per worker, which is k star, it will experience a larger change in k. This relationship can also be observed in the graph. Since the closer you get to the steady state, the smaller the gap which represents a change in k becomes. Since the gap in the beginning is y, the difference between investment and depreciation will be larger and you will move faster towards the steady state. As it nears the steady state, the gap becomes narrower and the difference between investment and depreciation will be smaller, causing the movement towards the steady state to be slower.